called this lesson various two-dimensional force problems. In particular, I want to talk about this first one, the lawnmower problem. I like the lawnmower problem. I like the lawnmower problem. Like, oh, heck, I'm just going to tell you blatantly. There's going to be a lawnmower problem on your test. What do we mean by a lawnmower problem? It's a situation where you're either pushing down on something at an angle, did I say angle? Or where you're pulling up on something at an angle, did I say angle? And specifically what that means is even though the ground is flat, the normal force is not mg. Or even though we're on an angle, the normal force is not equal to mg perpendicular. Perpendicular, of course it is. So it's situations where the normal force is not mg or the normal force is not mg cos. I like example one. I like example one. Example one is a nice question. The only problem is this diagram was misbehaving. It looks like it's floating a little bit above the ground. It shouldn't be. It should be touching the ground. So kind of just imagine that it's perfectly touching the ground there. Oops. What's this question wanting me to find? It says find the normal force. Let's call that part A. Find friction. Let's call that part B. Find acceleration. Let's call that part C. Hannah, any suggestions on how I might want to start out? I already got a little picture. Thank you, Captain Ob. This is a job for a free body diagram. What are the forces acting on this? Get the obvious one. And gravity is not going to be any kind of a funky component this time. What else? Now, normally, no pun intended, my next force would be the normal force. I'm going to tell you this one's a bit weird. Save the normal force for later. What I would jump to is the yucky force. In fact, often when I'm solving nasty problems, my strategy is I'll do the easiest thing first to get my mojo up, gravity, but then I'll jump into the yuckiest one. Also, because I've done the easiest one, often that gives me a reference to kind of figure out how the other ones are going to fit together. So I have this 200. I'll call that an applied force, but it's at an angle. Did I say angle? Guess what this is going to be a job for? What components? Because the ground is flat and gravity is vertical, rather than parallel and perpendicular, I'm going to go back to an older notation. I'm going to break this into vertical and horizontal. Hannah, is there friction in this question? So I think it's sliding to the right, so friction is going to be pointing to the left. The real question is, what about the normal force? Don't write this down. Why would this be wrong if I drew the normal force exactly the same size as mg? Why does that have to be wrong? So this is where I always said to you, is it sinking into the ground like quicksand? Is it flying to like Superman? No. Then the forces are, I'm looking for a word begins letter B. But if I want to be even more specific, it means that everything down has to equal everything up. Now, what is everything down? So what is everything up? If I was drawing this to scale, I would draw a normal force that was as long as those two arrows put together. I'm going to zoom out a little bit so I can fit this all back on a page. So if I'm going to draw the normal force, I'm definitely going to exaggerate it to make sure it catches my eye. And if I was really going to scale, I'd try and draw it the same length as those two vertical components. Hannah, what's A want me to find? Is it sinking into the ground like quicksand? Is it flying into like Superman? Okay. Who's winning? No one. It's balanced. So can you give me an equation? Everything up equals everything down. What's everything pointing up? Equals. Fy. You know what? Because it's our first time doing this particular situation, let's redraw that little triangle right here. Where I have F applied equals 200. This is 20 degrees. There's Fy. There's Fx. Hannah, that F applied, that 200, opposite, adjacent, or hypotenuse. What about Fy? Fx. Okay. Fy, I would use that. Which trig function has an O and an H in it? Sine? Are you saying, Hannah, my joy, that Fy is sine? Will that always work? I don't know. I'd have to do a lot more examples. But I've also just shown you how you can figure out the trig in about 20 seconds just by making a quick sketch. So if I'm hearing you correctly, Hannah, and I think I am, you're telling me that the sine of 20 would be Fy over F applied? How would I get the Fy by itself, FYI? So FYI for Fy, you're telling me that Fy is going to be F applied if I generalized sine theta? So now we can find the normal force. The normal force is going to be mg plus F applied sine theta. It's going to be 50 times 9.8 plus 200 sine 20. That's if we were pushing down. What if we were lifting up? What would that do to the normal force? Increase it, decrease it, or would it stay the same? It would decrease it. I'd have a slightly different equation and free body diagram. I'd have to do a little bit of thinking, but we'll do one like that a bit later. What'd you get on your calculator? I know you can type with one hand. 50 times 9.8 is 490. Sine of 30 is 0.5. Sine of 20 is going to be around 0.4-ish. 500, I'm going to guess around 560 something. What do you get? 558. Oh, you know what? Because I'm going to use this, I'm actually going to do this on my calculator because I'm going to want to carry the extra sig figs somewhere. So I'm going to write 558.404. And then I'll round off to 3 sig figs for my final answer, newtons. But I've got that just in case I need it. Good job, kiddo. Danielle, my love, what's B want me to find? Friction is what times what? I don't know the normal force. Oh, but wait a minute. Ha! Actually, the normal force is 558.404. But normally, no pun intended, I would have said, I don't know the normal force. And for a question this tricky, it's not like I can quite go, oh, but look, I don't know the force the same size as the normal force. What I can say is, well, it's not sinking to the ground. It's not flying in the air. I can come up with an equation, everything up equals everything down, and figure out what the normal force has to be. Hey, Danielle, what's mu? I don't know. What's mu with you? What's mu? 0.1 times 558.404. Hey, I don't need a calculator for this, Danielle. Multiplying pi by 0.1 is just the same as dividing by 10, right? So there was no need for me to go to my calculator. Why, I'll bet the answer is 55.8, right? Right. Because, I mean, all of you know how to multiply by 0.1 in your head, right? Right. C. Ooh, the acceleration. Who's winning? Please be very careful. Who's winning? Yes, not the 200. We're not going to use the 200. Fx is winning. Who's losing? Friction. What's that going to equal? ma. So I'm going to have this. Fx minus friction equals ma. Ooh, Fx. Which trig function? Of course it is. Oh, we'll take that. And if I'm not quite sure, really quickly here, I could say cos theta equals Fx over 200. Gabe, how would I get the Fx by itself? How will the 200 over? Oh, you know what? Let's generalize this. Instead of putting the 200, let's put F applied, and that way we have a one-size-fits-all. I'd multiply the F applied over. So you are correct. I can replace Fx with F applied cos theta minus. Normally I'd go friction is mu times the normal force, but wait a minute. Danielle, I know friction, don't I? It's going to be minus 55.8404. See how I got those extra sig figs in my head? Aren't I clever? Aren't I clever? Equals, oh, you know what? Divide by m. That equals the acceleration. Now, there is a possibility here that you get a negative answer. Really, Mr. Dueck? Pause for a second. Did you get a negative or positive? What'd you get? 2.64 meters per second squared. Maybe 2.63. Probably depends on how many sig figs you used or you carried. Okay. That's a lawnmower question. There's going to be one on your upcoming test. We'll either be pushing down at an angle, pulling up at an angle, or something like that. Let's do one more. Oh, here's one where we're pulling up at an angle. Okay. Wants me to find the acceleration. How am I going to start this one? Free body diagram. What are the forces acting on this? Get the obvious one. What else? Hold off on the normal force. Is there a yucky slanty force? Let's deal with that first. So I have F applied, but it's going up at an angle. Did I say angle? I'm going to break it up into Fx pointing to the right. And this time, Fy, instead of pointing down, Fy is pointing up. So what does that tell me about the normal force? Bigger, smaller, or the same size as mg? Smaller. Rather than go to scale, I really exaggerate it so it catches my eye, so that when I look at this later, if I get interrupted, my brain says, oh, that looks weird. Oh, I better be careful. Don't you dare say, oh, but look, another force the same size as the normal force. I'll have to do some number crunching. They gave me a mu, so friction is pointing that way. Here they want me to find the acceleration, so let's jump right into it. Who's winning? Fx? Who's losing? What's that going to equal? Ma. Looks like I have hypotenuse. Oh, instead of red, Mr. Dueck, let's use a different color. Hypotenuse, Fy, opposite or adjacent? Opposite, Fx, adjacent. Yeah, it's right. H and A, although I would go A and H. I agree with you, though. Which trig function? Yeah. So, which trig function, Ethan? Which trig function is A and H, Ethan? Is correct. A and H, I agree. But which trig function is that? Cos, you say. So, this is going to be F applied cos theta that all right? Minus mu times the normal force. I don't know the normal force. Ugh. You know what? Over here in the margin, let's do a normal force equation. Ethan, are we sinking into the ground like quicksand? Are we flying into the like Superman? No, you say? Then everything up has to equal everything. So what is everything up? So the normal force is going to be mg minus Fy. Which trig function was Fy, FYI? So it's going to be F applied sine theta, and that can now go over here. So friction equals mu times mg minus F applied sine theta. That would equal MA. They want me to find A, so with your permission, Ethan, I'm going to put the A equals on the left-hand side and divide by M. Haven't used any numbers on purpose. We're trying to generalize, but now let's make it ours. How big was the applied force at an angle? Was it 18? Yes? I'm going from memory here. So it's going to be 18 cos 21 degrees minus, what was mu? Was it 0.23? And then this is complicated enough. I'm going to use a square bracket. 7 times 9.8, take away F applied, 18 sine 21 degrees, close off the square bracket, all divided by 7. This is one I would encourage all of you to try typing in, because if you can't get this answer after doing all the work, that is throwing away marks. On my calculator, I have to really track some brackets. Is this a fraction? Yep. More than one thing on the top? Yep. Bracket 18 cos 21. Then I have to close off the cosine, minus 0.23. I open a second set of brackets. 7 times 9.8, take away 18 sine 21. I have to close off the sine. Then I have to close off the normal force bracket. Then I have to close off the top, divided by 7. I think I typed that right. Do you get 0.3585844269? Yeah? So 0.359, if I round off properly. Whew. That was kind of neat. So lawnmower questions. You'll have several of those in your homework as well. Another neat application is called static equilibrium. An object is in static equilibrium if it's at rest. In other words, not only are all the forces acting on it balanced, because if it's at rest, the acceleration is 0. It's not moving at all. And a classic static equilibrium question is the street sign question, where you have a sign hanging from 2 cables, one of which is at an angle. Did I say angle? So something like this. An object, it says, at rest has 0 acceleration. So if you have no acceleration, that means the forces on you are I'm looking for a word that begins with letter B. That's what Newton's first says. That also means the forces add up to 0. If you were to add them, they add up to 0. If you were to add them, what do they add up to? Remember that. It says find the tension in both cables. One way to do this is with components. I'm going to argue against it. This is the first time now, Justin, where do I see angles? I'm going to say to you, yeah, there's a better method than components. Components are not the end-all, be-all. You can't have angles components as a reflex. You got to think about it a little bit. You know what it's a job for? Except I'm going to do a free body diagram not on the mass. I'm going to do a free body diagram right there where they all join. What are the forces acting at that spot? Get the obvious one. So I have mg. What else? How many cables do I have? How many tensions then do I have? I'll call this tension 1 to go with cable number 1. I'll call this tension 2 to go with cable number 2. Yeah? There's my free body diagram. How am I going to solve this? What do these forces add together to give me? I'm going to add them together. How would I add vectors together? Draw them. I'm going to go tip to tail rather than components here. It's going to work better, and you're going to see why in a second. What's my vector triangle going to look like? I always start, as I said a few minutes ago, with the easiest force first. What's the easiest force out of these three? I'm going to draw gravity down. Yoink. I always draw the yuckiest force next. What's the yuckiest force? The upwards at an angle tension 1. And here's my big advantage. What do these three forces have to add to? Because they're in equilibrium, 0. What do they have to add to? 0. What will that look like in a vector triangle? 0 in a vector triangle is a triangle where I end up right back where So watch. If I stopped drawing right here that long, don't write this down, and then I go straight horizontal, because this one is straight horizontal, did that get me right back to where I started from? Tell me when to stop drawing cable 1. That's going to be tension 1. And here is tension 2 coming right back to where I started from. By the way, what I haven't done, Graham, is I haven't added these two tip to tail, because the resultant would go that way. What I've done is I've added 3 vectors together, and I knew the answer ahead of time. It had to be 0 because this thing's not accelerating. What does 0 look like in a vector triangle? Right back where you started from. That's why that arrow points right to where I started from. Why is that so nice? Well, I noticed this 35-degree angle is between an angular line, a slanty line, and a vertical line. I'm pretty sure that 35-degree goes right there, because that's between a slanty line and a vertical line. I didn't use geometry there. I was just kind of clever by saying this angle must show up. Tension 1, opposite adjacent or hypotenuse. Tension 2, mg. You know what, Mr. Dueck? I think since we haven't done this in a long time, maybe we should write the word SOHCAHTOA on the page. Okay. It wants me to find the tension in each cable. I'll find tension 1 on the left. I'll find tension 2 on the right. Which force do I know? So I'm going to use mg to find the other ones. So to find tension 1, I'm going to use AH. Aisha, which one? Cos, you say. So as a trig function, it's going to look like this. Cos theta equals mg over tension 1. Aisha, what am I trying to find? How would I get tension 1 by itself? It's on the bottom. Or is it? Well, here's what we said. We said dividing by tension 1 on this side is the same as multiplying by tension 1 on this side, and then you can divide the cos over. So we ended up with mg over cos theta. It's going to be 10 times 9.8 over cos 35. 10 times 9.8 over cos 35. Do you get 119.63, 120? Is that right?
Yes.
Yeah. You would be using this math if you, for example, were a company that hung road signs by businesses, because you'll sometimes see signs that are on angles, although often there's no 90-degree angle right there. It's a bit trickier. And you'd probably triple this for protection or quadruple this for protection for your cable strength. You wouldn't just exactly go to 120. You'd build a massive safety margin in to take into account wind and other factors. Chloe, which trig function will I use to find T2? Tan, you say. Tan, you say. Tan. Okay. That sounds like a good idea right about now. A little tan somewhere would be great. Oh, sorry. Welcome back. 35 equals opposite over adjacent. Chloe, how would I get the T2 by itself here? Yeah. Remember your trig coming back to you, I hope? It's going to be 10 times 9.8 tan 35, and I get 68.6. Now, there is another way you could have done this. Don't write this down, just look up. You could have done this with components, which is the slanty line. You could have broken this up into a horizontal and a vertical component. You could have realized that these two are the same size, and so you would know how big this vertical component was by going, it's equal to mg. You would go 10 times 9.8. Oh, this is 98 newtons. And then from that angle, you'd be able to figure out how big this had to be and how big that had to be. I don't think it's faster. I kind of like this. No one wrote that down. I'll bet you'll write this down. I would like to, but I'm having to cut corners a little bit because we're behind schedule. So I think I already told you, although there's some questions in the homework that want you to find angle theta, I'm not going to be asking you to find angle theta on this test. It would be shift sine or shift cos or shift tan, but I already assessed you on that a little bit. And I would love to do the static equilibrium problem, but I've got to cut corners somewhere, so no static equilibrium questions on your test. Newton's first law, understanding that if you're not accelerating, the forces are balanced, that's fair game, but I won't be giving you a two-dimensional slanty one like this. And so what that means is we can skip example 5, although it's cool. It's kind of the physics of rock climbing. And we can skip example 6. So what's your homework? Here's what I assigned my block A's. One, two, three. Four, although for number 4, I think I would break that 60 up into components. Parallel and perpendicular this time. Number 5, although in number 5, just find the acceleration, please. So you can cross out, find the normal force, and cross out, find the net force down the ramp. Seven, can skip 8. You can skip 9. You can skip 10. 11 is good, though. That looks like a lawnmower question. 12 is good, though. That also looks like a lawnmower question. You can skip 13. You can skip 14. 15 is good, though. That looks like the lawnmower question. And 16. And that, my angels, is forces. You're also now capable of doing any question on the ultimate review.